Good morning. Today we will discuss principal component analysis. Principal component analysis, PCA. So let us see the content of today's presentation. First we will describe the basic concepts prevailing with principal component analysis. Then we will see that how principal component can be extracted from a given data set. Then we will go for sampling distribution of eigenvalues and eigenvectors. You will see that eigenvalue eigenvector decomposition of the covariance or correlation matrix is the means for extracting principal component. Then followed by model adequacy tests. Then we will describe one case study. I think it requires around 2 hours of lecture. First hour we will try to complete up to extracting principal components. So, what is principal component analysis? So, principal component analysis is a data reduction technique. Data reduction technique. It is extensively used and developed by Hotelling H in 1933, and it is the data reduction is done with two perspectives in mind. One is that lower dimension, second one is orthogonality of the new dimensions. Orthogonality of the new dimensions. Okay. New or transformed dimensions, which are basically PCs, principal component. So, let us now go for a very simple two-dimensional plot. For example, let our data set is X, which basically composed of n cross 2, that means n measurements on 2 variables. So, like this. So, this one is variable x1 and variable x2, then this one x11, x21. So, like this xn1, then x12, x22, so like this xn2. Okay. If you plot the data here, suppose this axis is x1, this is x2. Now, if you plot the data, let us assume that the data is like this. Data plot looks like this. Okay. Now, if you compute the covariance matrix of X, you will be getting, as we are talking about data. So, we have collected a sample, in that sense we have to write. So, this will be S11, S12, S12, S22. So, 2 cross 2 matrix. So, this scatter diagram this scatter diagram shows that there is relationship between x1 and x2. So, if you calculate correlation matrix between for x, what will happen? You will get certain correlation coefficient. This will be your correlation matrix 2 cross 2. You will find out that R12, that will be, as you know, that correlation coefficient varies from -1 to +1, and here x2 and x1 the relationship is positive. So, you will get it is a quite large value, meaning maybe it may be almost equal to 0.9 here, 0.90. Getting me? So, this is one aspect, that we have taken 2-dimensional original data x1, x2, their scatter plot looks like this, and it shows there is relationship, primarily linear relationship, and if you go for correlation matrix, you will be finding out the relationship is strong enough. Okay. This is first. Second issue here, if I want to see the variability of x1 and variability of x2, then these are S11 and S22. This is the variance component. Now, if we go for that, this is sample, suppose population covariance, then what will happen? This will become sigma 1 1, sigma 1 2, sigma 1 2, sigma 2 2. Now, this population variance component for x1 is this sigma 1 1, and for x2 is sigma 2 2. If we see the scattered here, if we say that n is representative enough for the population large value, if we see the scattered here, then you see that the across this x1, this is the range, variability range. Similarly, if you see across x2, so you will be getting another range, that is variability x2. Okay. So, you see that definitely the x2 and x1 variability are not same, but they are substantial values. That means, if this is my diagram, this is my relationship, then definitely S11 and S12, S11 and S22 for x1 and x2 respectively, this value is high. Correct? Now, let us see that another, okay, the same diagram. Let us see that you are rotating this axis x1 and x2 anti-clockwise, rotating the axis x1 and x2 rigid rotation, keeping this origin, this one rigid by angle theta. Then what will happen? You will get new direction for x1 and x2. Correct? If I rotate x1 by theta, then x2 also will be rotated by theta. Now, if I say in the new direction, this one is z1 and this is z2, this one is z1 and this is z2, then what can you say about the variability of the data set along z1 and z2? Getting me? So, if I draw one more figure along z1 and z2 here, then suppose I am writing this one. So, you basically in this, what I am doing now, this Z1 is this along theta. Now, I am just making it like this, so that it will be, we will be able to see it clearly. Clearly in the sense, correct. If you see the scatter plot now, this one is Z1 and this one is, other one is Z2. I think it is like this only, correct. Now, if we see the variability across Z1, this is variability of Z1, and similarly if you see this one across Z2, you are getting this variability across Z2. What are you getting here? If I plot both the figures now, here, so basically you got something like this. This one is x1 and this is x2, and we have seen that variability of x1 and variability of x2. Okay, so this is our original data dimensions, and this is, as we have rotated by theta degree anti-clockwise, we are saying that transform data. Getting me? Transform data. Now, it is clear from these two diagram that although here from variability explanation, variability of x1 and x2 point of view, if I see that they both are large and maybe x1 variability is little more than x2, but if I go by this z1 and z2, what I am finding out, variability across z1 is much more than variability across z2. So, what we have got then, variability across z1 is greater than variability also across z2. Second thing is that, this is one. Second issue is here that here in x1 and x2 both the variables are correlated, that is why you are getting an ellipse, bivariate ellipse inclined one. That means this, if I see the ellipse here, the major and minor axis of the ellipse are not parallel to x1 and x2. It shows the dependency between x1 and x2. Now, here in the transformed case, what is happening, major axis of the ellipse is across z1, minor is across z2. This shows z1 and z2 are independent. That is what I said, the orthogonal dimension. Orthogonal dimension or orthogonality is preserved. Okay. Now, can we do this? Is there any mathematics by which we can transform a correlated structure, data structure into uncorrelated data structure, as well as from correlation, that means to in the reduced dimension. Why reduced dimension? If the variability across Z2 is much less compared to Z1, then what will happen? We can say that the information content across this Z2 dimension is very less. We can ignore this information, we can just capture the information here. In statistical sense, information is the variability, variance part. So, Z1 alone is sufficient to give us the information what is available in the original data set. If this is the case, I will go for only one dimension, that is Z1. That is what is the reduction. So, principal component analysis will do this, not necessarily for the 2 dimensions, it can be done for p dimensions. By p dimension, what do you mean? That your X data matrix is n cross p. Okay. That means the variable you are considering, X variable is x1, x2, there are p variables, p can be quite large, it may be 50. So, we are now converting, what you are doing, this x is converted to z. If x is p variable case, p cross 1 vector, z can be p cross z also, we can extract, suppose z is m cross 1 vector. So, m can be less than equal to p, okay, depending on the correlation structure, the matrix will be using that rank of the matrix and all those things. Okay. But essentially what we want, basically we want that m should be less than equal to p. If p is very large, m should be as low as possible compared to p. So, that is what is done in principal component analysis. Getting me? So, principal component analysis is a data reduction technique. It transforms the original data matrix or data set into some other dimensions of reduced that components, and it preserves the orthogonality of the components. So, as a result, what will happen? What are the advantage you will be getting from here? Advantage is, suppose we want to do a prediction model using multiple regression, and my x variable, these are all IVs, independent variables. If IVs are correlated, then that ultimately leads to multicollinearity problem. Multicollinearity issues are there. So, under multicollinearity condition, the regression model what you want to fit, that y equal to function of x linear model, this model will not be a good one, because under multicollinearity it may not be possible to estimate the parameters. If you use estimate, what will happen? It may be, there may be distortion, so many things will be there. Okay, there are different ways to do, for example, ridge regression can be done in case of multicollinearity problem, but my question is, if I can make them independent, then these IVs x can be transformed to this z scale like z here, these are truly independent. So, now you can fit a model using f z, getting me. So, these are the advantages. Now, what is the principle, basically how these things, that data reduction here or the orthogonal reduction, that is dimension orthogonality of dimension is maintained and data is reduced to lower dimension, what is the method? We will go by the 2 by 2 matrix case for S. So, the same 2 dimensional case. So, if I see this, okay. So, you have seen that we got a ellipse like this in the original data set x1 and x2, correct. Now, let us think that there is one point M, okay. This, for example, let this coordinate is x1 and x2, x1 for x1 variable, x2 for x2 variable. Okay. Now, what you have done when you are converting to z, when you are converting to Z, that means Z1 and Z2. So, this is Z1 and this one is Z2. So, I am writing this point little above, for example, let it be here, this point. Okay. This is the point. So, you have rotated x1 by theta anticlockwise and this also theta. I want to know, first you say what is this point, this value here. If m is x1 x2, then this value is x1 0. For example, let this is m1 point on the x1 axis. Similarly, if you project this m, that projection on this point, projection on x2, what we will get? You may get a point m2, what is 0 x2, this coordinate geometry. Okay. Now, what we want? We want to find out what is the projection of this m1 on z1 as well as z2. Getting me? So, you just let me draw this axis now clearly. What you want here? So, this is your theta, our aim is we want to find out this is this one x1 0. I want to find projection of m1 on x2, z2 and z1. So, what do? You will find draw a perpendicular here. From this point you want to draw a perpendicular. Okay, so, from this point draw a perpendicular here. Similarly, you want also from this point you want to draw a perpendicular line here and perpendicular line here. What you are doing now? That x1 component is projected on z1 as well as z2, x2 component is projected on z1 and z2. Now, this angle is theta, this is theta. If this one is theta and your this also theta, so this will be theta. So, ultimately what you will find out that the projection of m1 on x1 will be x1 cos theta. Okay. So, if I write z1 here, there are two projections, one is from x1 cos theta. Similarly, there will be another projection that is a plus x2 sin theta, x1 cos theta plus x2 sin theta. Okay. So, similarly, in the z2 axis what will happen, that minus x1 sin theta plus x2 cos theta, simple trigonometry. So, you will be able to find it, only just know the theta. Once you know the theta, you know the triangle and project it. Okay. So, then this one, if I write in matrix term, I can write like this: z1 z2 equal to cos theta sin theta minus sin theta cos theta into x1 x2. You can write like this, because z1 equal to cos theta x1 cos theta plus x2 sin theta, z2 equal to minus x1 sin theta plus x2 cos theta. This equation you are getting. Okay. So, then I can write this one equal to z equal to A transpose x, where z is nothing but this one z1 z2 and A transpose, this one we are saying A transpose, this is A transpose and this is your x and this is your z. So, if I do like this, then A transpose equal to our cos theta sin theta minus sin theta cos theta. So, then what is the A matrix? Transpose of transpose, this will be cos theta minus sin theta cos theta. This row transformation is there. Okay. So, instead of p equal to 2, if there is p equal to p, what will happen? You will get Z1, Z2, Zp, that will be your Z, and your this equal to A transpose. So, A transpose, I am now writing that like this, our A is A1 here, this is nothing but this column, and A2 is this column. Okay. So, if there are p variables, there are 2 variables, so that is why you are getting this one is equivalent to A11, this is equivalent to what we are saying A11 x1 plus A12 x2. So, this is A12, and this one is A21 and A22. You can do this in theta, cos theta, sin theta we have written here. In place of cos theta sin theta, I am writing that this is A11, A12, A21, A22 like this. So, if there is p variable case, so you can write down like this A11, A11, A21, yeah, this is transpose, A transpose. So, A11, A12 like this, A1p, A21, A22 like A2p, similarly P1, P2 like APP. This is your P cross 1, this one is your P cross P, and then your x1, x2, xp. So, there have been these 2 dimensional, this case. Now, we are making like this and we are writing in terms of A's. So, this if I write further, I can write this one is A transpose X, what we have written earlier also. Okay. Then what we want to see that how this, that we say that it will be orthogonal transformation. So, how this orthogonality is maintained here with this 2 dimension case we want to see. What we have written for the 2 dimension case, A equal to our cos theta sin theta minus sin theta cos theta, that we are saying we can write like this A1 and A2. Getting me? Now, then what is your A1? A1 is cos theta sin theta. Now, if I want to know what is A1 transpose A1, what will be the value here? Cos theta sin theta into cos theta sin theta will be cos square theta plus sin square theta will be 1. Getting me? So, similarly, you will be getting A2 transpose A2 equal to 1. Correct? Now, then if I want to know that what is AT transpose A, that will be cos theta sin theta minus sin theta cos theta into A is cos theta sin theta minus sin theta cos theta, 2 cross 2, 2 cross 2, cos sin plus cos square theta plus sin square, that will be 1. Now then cos minus sin minus cos, this will be 0, 0 1. Okay. So this will also be, if you do A transpose, you will get the same thing, correct. And see, this is a symmetric matrix in such a way that if you do like this A inverse A, you will also be getting same thing. That means this is identity matrix. So that means what we are getting, A inverse A is I. When A inverse A is I, this is what is orthogonal. That off diagonal elements are 0. So you are getting orthogonal transformation. Okay. And this transformation matrix, this is orthogonal transformation matrix A. Okay. Now what we will do, I will show you one slide here. You see that there are p variable for x, and you can extract p principal components z1, z2 to zp, and the equation will be like this. What we have seen then, what I mean to say, if you just see this our earlier development, that I think I told you here, z1 equal to a11 x1 plus a12 x2 plus a13 x3. So like this you will be getting. So what you will be getting, z1 equal to a1 transpose x, which is a11 x1, a12 x2 dot dot a1p xp. Similarly z2 a2 transpose x, 21 x1, a22 x2 like a2p xp. So if you write down here zk or zj, you write, let it be zj, then aj transpose x, aj1 x1, aj2 x2 dot dot ajp xp. So following, if you go up to the last principal component that may be possible to get, that is AP transpose X, which is AP1 X1, AP2 X2 like APP XP. Okay. And we said that we want orthogonal transformation. So when you are reducing the dimension, the principal components are, we want this type of AJ transpose A equal to 1, that is one thing. Second one, what we want? We want that when we are extracting the principal component Z1, which is the first principal component, the variability in Z1 must be the maximum, what we have discussed earlier in this explanation. We say we want the first principal component in such a manner that it will explain the maximum variance possible. Second principal component will explain the next maximum variance followed. Similarly, third one like this. So, if this is the case, then I can say here variance of Z1 greater than equal to variance of Z2 greater than equal to variance of ZP. So, what we will do then, we will just 1 minute. So, I have shown you this thing and that this is possible, and now we want to find out what will be the principal components given a data matrix X, how to extract the components. Fine. So, here before going to this extraction part, I have to tell little bit of that we are saying that in general we are saying Zj is Aj transpose X, where Zj is the jth principal component, this is jth PC, and this Aj and X, what are those Aj and X, you will be X, you know what is this Aj, we will be defining later on. It is, but if you see the equation, it is similar to like regression coefficients, A11 x1 plus A12 x2 plus A1 p xp, similar to regression coefficient, but it is not. So, now I want to know, I say that variance of Zj you require to compute, because variance of Z1 greater than variance of Z2 like this. What will be the variance of Zj? It will be variance of Aj transpose X, then it will be Aj is the constant here. So, Aj transpose variance of X Aj. As we know, this is a vector basically, Aj is a vector. Later on you will be you know that Aj1 to Ajp, that is the vector. Now, what is the variance of X? X is, what is the variance of X means, that will be the covariance of X. So, covariance of X will be sigma. You have seen earlier in different class, sigma 1 2, sigma 1 p, sigma 1 2, sigma 2 2, sigma 2 p, that is sigma 1 p, sigma 2 p, sigma p p. So, that means this will be Aj transpose sigma Aj. Okay. Then what will be the expected value of Zj? Expected value of Zj will be expected value of Aj transpose X, which is Aj transpose expected value of X, which is Aj transpose mu, because we said that X is p variable vector and it has p mean vector, mu 1 to mu p, correct. So, that means essentially that Aj transpose X, which is something which is having Aj transpose mu, Aj transpose sigma Aj, that is the mean and variance part. Okay. So, if they are normally distributed, then you will put normal n. So, Aj transpose is 1 cross p. Now, what will be your mu part? Suppose this one, if you want to do 1 cross p into p cross 1. So, 1 into 1, okay. And this one also will be 1 into p, p into p, 1 into p, that is 1 into 1. So, this Aj transpose X, this one will give you a univariate case, because linear transformation of variable X. So, all the principal components are linear transformation, okay, that AJ transpose X, that is the linear transformation. Okay. Now, if you do not get the values of sigma, capital sigma as well as the mu, because these are population parameter, that is mu and sigma. If you know mu and sigma and then given a data matrix you go for this type of that extraction of Zj, then this will be known as population PCA. Getting me what I mean to say? If you know mu and sigma of the population, that X variable case, then you are doing population principal component analysis, but it is seldom known. You will not get these two values. So, what is the then the rescue? Rescue is you will use x bar as estimate of mu and S as estimate of sigma. So, when we use S, actually here we will be playing with the covariance matrix. So, if you use S, capital S, which is the sample covariance matrix, then your principal component analysis will be known as sample principal component analysis. So, we will be writing this as sample PCA, and essentially population PCA is not possible. So, we will go for sample PCA, because when you are talking about applied principal component analysis, then we have to rely on the data and we will go by sample PCA. So, next we will discuss sample PCA, that means how we will extract all those things. Okay. When we use sample PCA, then your expected value of Zj will be expected value of AJ transpose X. Okay. So, this will be AJ transpose expected value of X, which will be AJ transpose X bar, okay, from sample point of view. Similarly, your variance of Zj, this will be your variance of AJ transpose X, which will be nothing but your AJ transpose covariance of X AJ. This is AJ transpose. Now, covariance of S will be replaced by capital S AJ. Correct. So, if I say that okay, this can be normally distributed, then AJX, it is normally distributed with AJ transpose X bar, AJ transpose S AJ. Okay. Now, I will explain you when we extract PC, what are the principles we follow. Getting me? We will discuss the principles now. Now, let us see the slide. Each PC is a linear combination of x1, linear combination of x, a p cross 1 variable vector, that is AJ transpose X. You have seen this one already. First PC is A1 transpose X subjected to A1 transpose A1 equal to 1, that also we have described, that maximizes variability of this variance of A1 transpose X. Second PC is A2 transpose X, that maximizes variability of A2 transpose X and subjected to A2 transpose A2 equal to 1 and covariance of A1 transpose X, A2 transpose X equal to 0. Keep in mind this one. What is happening? We are saying first component you are extracting, that is our Z1 is the first component, which is A1 transpose X. You will extract in such a manner that the variability of Z1 will be the maximum, and also A1 transpose A1 equal to 1, that is the normalization case. So, I have a data set, So, and in this, suppose this is my total variability portion. So, Z1 will extract as max as possible by Z1. So, let Z1 variability extracted is this much. Then I am coming to the second PC, which is my A2 transpose X. Here what happened, the remaining variance, I want to extract maximum of the remaining variance. So, variance of Z2, that is the maximum of the remaining. So, let I am able to extract this one Z2. See, ultimately if this is my total variability, Z1 and Z2 has already maybe around 70% is extracted by the two components. There are P components. Okay. This is also here A2 transpose A2 equal to 1, and covariance of A1 x A2 x this equal to 0, because orthogonal components. Now, in this manner, if you go for Zj, then you will write Aj transpose X. Here you will definitely maximize the remaining variance. Already J minus 1 components are extracted, the remaining maximize this one, the remaining variance, and here also you will write Aj transpose Aj this equal to 1, and covariance of Ajx Akx this equal to 0 for k less than j. Why k less than j? What I am saying, you are means k up to k can be 1 to j minus 1. So, when you are extracting this, please keep in mind this is the principles. What I am saying, that when you are extracting the first component, that basically takes care of the maximum variance of the data set subject to this normalization. Then A2 Z2 second principal component goes for the second max of variability of the remaining variance, and subject to this as well as covariance component between the first two, that will be 0. When you go for the third, there also you will maximize the variability of that component subject to the remaining variability, and you also make a normalize it, that A3 transpose A3 equal to 1, and covariance between A3 A1 as well as A3 A2, that x is common, that will be 0. So, in the same manner you will extract. Okay. So, then essentially what we are doing now, actually if I go by the general component, that is Zj, this is my Aj transpose x. We want to maximize the variability of this, which is our Aj transpose S Aj. Now, I am using sample covariance matrix, and subject to what we are saying, that Aj transpose Aj this equal to 1, correct. So, we have two things, first one we want to maximize this, second and we have this constant. So, this second one I can write like this, Aj transpose Aj minus 1 equal to 0. As we want to maximize this with respect to this condition, so what we can do, we can create a function, suppose this function is L, which is Aj transpose S Aj minus lambda into Aj transpose Aj minus 1. correct. So, we are using a function, this is the Lagrange, L lambda is the Lagrange multiplier. Lambda is Lagrange multiplier. So, you know that this is the general way of maximization process using Lagrange multiplier. So, what you require to do now? You require to find out the AJ value in such a manner that this function will be maximized. So, that means what I want del A by del AJ, that is what I want, getting me. So, this you want to put it 0, provided del to L by del AJ, that will be that matrix you will also get, and it should be the maximization that positive definite and negative definite case is there. So, that condition must satisfy. So, this ultimately results into this equation. It will be like this: S minus lambda I into AJ equal to 0. See, this is, if you take derivative with respect to AJ, it will be 2s AJ. If you take derivative with respect to AJ, it will be 2 lambda AJ, this derivative. So, ultimately it will be 2s AJ minus 2 lambda AJ, that equal to 0. So, 2 will be cancelled out, that 0 is there. So, S minus lambda, but S is a matrix, lambda is a scalar, this into AJ equal to 0. So, that is the equation. Okay. So, now S is your P cross P matrix, because P variables are there, lambda is a scalar, it all depends on that what will be the number of lambdas, but I definitely it will be P cross P matrix. Okay. Then this equation is a famous equation in matrix algebra. You will find out that set of linear equations case, suppose, and more famous one is this one. Suppose I want to know the lambda values, then what you require to do, you have to find out the characteristics equation, this equal to 0. So, determinant of this equal to S minus lambda I equal to 0, determinant of this equal to 0, this is a characteristic equation. Getting me? So, if S is P cross P, then this equation has P roots. That means, you will be getting lambda 1 with the condition greater than equal to lambda 2 like this, lambda P. Okay. So, let us see now some more slides here. So, I said that this will be that pth order polynomial is there, P roots you are getting, and you have to, this is the if you know lambda, so basically from this equation you will be able to find out the lambda values. Now, take 1 lambda, put into this equation, and then you find out the A values. Okay. And I will show you one data set now. This is the data set, what is the profit and loss for the example we have started with, and if you plot the scattered, what you are getting that it is almost linear relationship. So, that means here data reduction is very much possible. So, we tried with 2 variable case, and what we found out that these are the things. So, first is the covariance matrix. Covariance matrix is S, So, with this example S is 1.15, 5.76, then your 5.76, 29.54. Now, what we want? We want S minus lambda I determinant equal to 0. So, your I will be 2 by 2 1 0 0 1, I is identity matrix. So, if I do like this minus lambda I, so that means instead of lambda I am writing 1 0 0 1. Okay. This total determinant if I write and if I put into 0, so then what is the resultant in this one? 1.15 minus lambda 5.76, then 5.76 29.54 minus lambda, this equal to 0, determinant of this equal to 0. So, ultimately you will be finding out 1.15 minus lambda into 29.54 minus lambda minus 5.76 square equal to 0. It will be it is a quadratic equation of lambda, because our S is 2 cross 2. So, there will be 2 roots. So, lambda 1 and lambda 2. So, the two roots will be the 2 roots of lambda, let it be lambda 1 and lambda 2. Now, using this equation you can find out. So, what I mean to say, the resultant equation is 1.15 into 29.54 minus 1.15 lambda minus 29.54 lambda plus lambda square minus 5.76 square equal to 0. So, lambda square minus, you add these two, 9, 6, 30, I think 30 point this lambda, this one, then this 2 is to be added, that you will be getting some value, this 29, this will be some positive value you will be getting. Okay. If I consider this as C, then your lambda is minus B is 30.69 minus B plus minus root over B square minus 4 AC, A is 1, C by 2 into A is 1. This will give you the eigen values, two values, lambda 1 will be your 30.66 and lambda 2 will be 0.03. Correct. So, you are getting your lambda 1 and lambda 2. Then what you require to find out? You require to find out the A values. So, what you will do now? We know S minus lambda I A j, that will be equal to 0. Okay. So, here we will be using lambda j now. So, as lambda 1 equal to 30.66. So, you put S is 1.15, 5.76, then 5.76, 29.54, this minus lambda is your 30.66 and into this matrix 1 0 0 1. Okay. This matrix, this into A1 equal to 0. Now, your A1 will be what? A11, A12. because there are two variables. So, I can write A11, A12, A11, A12, that will be 0, this value will be 0, but what will happen ultimately, you will be getting two equation and you will not get unique solution, you will be getting infinite solution under these conditions, because this equation is 0, this equation is 0, any value any. So, that means there will be infinite number of this A1. So, in order to restrict that, what we will do, A1 transpose A1 equal to 1. So, if A1 transpose A1 equal to 1, then what will happen, A11, A12, A11, A12, that is 1. So, A11 square plus A12 square equal to 1. So, whatever equation you are getting here, that the earlier equation, you put A11 equal to, when from this equation what is the value you are getting, you will be getting positive and negative values. So, you put this one. Once you put into this equation for A11, now A12 will be replaced by A11 for from this first equation. A1 is already there and our A1 relation you will be getting from here, from this you will be getting, because this is 2 by 2, this into this plus this into this. So, it is a two variable equation will be like this, some value into A11 plus some value into A12, that will be 0, like this. So, similarly, now you are getting one relation from here, suppose this is your P and this is your Q, then you are getting A11 equal to Q by P minus A12. Here you put, instead of A11 you put minus Q by P square A12 plus A12 square plus A12 square equal to 1. You will be getting A12 and putting here you will be getting A11. Similarly, A21 and A22 you will be getting. Okay. So, the final one, this is the, that is why this is your A11, A12, this is A21, A22, and you are getting this principal component Z1 and Z2. Okay. This is the manner of extraction of principal component.